Morgen. Mein Name ist Marlene Luckner. Ich bin der Marketing Manager der Firma ACAM Systemautomation. Ich darf Sie herzlich zu unserem Webinar zum Thema Simcenter, Simulation und Testing begrüßen. Wir möchten Ihnen im Rahmen dieser Webinarreihe einzelne Lösungen vorstellen und Ihnen einen ersten Einblick in Anwendungsmöglichkeiten geben vom Programm Heeds. Good morning, my name is Marlene Luckner. I'm the Marketing Manager from ACAM Systemautomation and I wish you a warm welcome to our seminar about Simcenter, Simulation and Testing. Als innovatives Unternehmen unterstützt ACAM seine Kunden seit 1994, vor allem in den Bereichen Produktentwicklung und Herstellung und liefert Lösungen, die den kompletten Produktlebenszyklus umfassen. Wir sind stolz, den Smart Expert Status zu tragen, eine Auszeichnung, die nur wenige Partner von Siemens Digital Industries erhalten und sind ca. 40 Mitarbeiter in 3 Standorten in Österreich. Ab 1. Dezember beziehen wir außerdem unseren neuen Standort in der Brauhausgasse in Leoben, da wir mehr Platz für unsere Ideen benötigen. Wir bieten aber nicht nur ein umfangreiches Moment. Ich muss da kurz was machen. So. Entschuldigung. Ich hoffe, das funktioniert. So. Wir bieten aber nicht nur ein umfangreiches Portfolio das umfangreiche Portfolio von Siemens Software und Hardware an, sondern können außerdem mit professioneller Leistung von Experten dienen, die Sie aktiv dabei unterstützen oder auch die Simulation und Testing für Sie durchführen können. As an innovative company, ACAM is supporting its customers since 1994, primarily in the areas of product development and manufacturing. ACAM offers integrated solutions that cover all phases of the product lifecycle. As top partner with the Smart Expert status from Siemens Digital Industries, we have round about 40 employees at 3 locations in Austria, and do not only offer you the extensive portfolio for software from Siemens and hardware. On top, we propose services from professionals who support you or can do the simulation and testing for you. Die ACAM Systemautomation und ihre Tochterfirma ACAM Engineering sind die perfekte Kombination von Software, Hardware und Dienstleistungsanbieter. ACAM Systemautomation and its subsidiary ACAM Engineering are the perfect combination between software, hardware and service provider. Aber genug von meiner Seite. Ich möchte jetzt ganz herzlich Jean-Bert Roux begrüßen, einen Experten im Bereich Heeds, der Ihnen dieses Programm oder diese Software näher bringen wird und die damit für Sie verbundenen Chancen präsentieren wird. A warm welcome to Jean-Bert Roux, who will present you Heeds now. Okay, Jean-Pierre.
Thank you, Marlene, for the introduction. Thank you, everyone, for attending this session. I'm going to share now my desktop screen. So now you should be able to see my desktop screen. Here we go. Thank you for the introduction again, and thank you for your time. In this session, we will talk about how you can leverage in a better way, your engineers, your designers, along with your software, CAD and simulation software. So this is basically the agenda I will follow. A few words about what we think is design space exploration, what is the solution Heeds MDO, how it incorporates within Simcenter solution. I will share also some application examples from different industries, different application to motivate ideas to yourself, how you could apply that to your own product and own methodologies. And we can finish with some questions if you have any. So what is design space exploration, and also what is about multidisciplinary design analysis and optimization? Those are 2 linked aspects. I would like to start with a little bit of, let's say, history over the past, let's say, 20, 30 years. Simulation has been used with an increasing manner. At the very beginning, we would use simulation to validate a given design or try to correct a troubleshoot. So, for example, a part failure on the field, you would try to understand through simulation why it would have failed. And over the time, with improvement of the software, more computation power, more methodologies, and more investment in engineers, we are at the stage where we can proactively use simulation to predict the behavior of any design. Well, I could moderate that in the fact that we still need to work on model calibration or correlation against tests. But basically, if you define a good methodology, you'll be able to have a digital twin that helps you to predict again the behavior of any product. So yeah, using this the simulation as of course enabled companies to operate with reduced time and reduced costs, because of course you don't need to do multiple prototypes over the development of a product. But now we are at the edge where because you have methodologies in place where you could think about automating those methodologies, such as everyone is using the same, such as no human error is being done. And automation means that it could be run behind the scene on your computer while you're doing more added value tasks, not repeating them over and over when you're doing iterations. So automation would be the first step. And then once you have automated your workflow, you could actually explore the design space with some smart search technology we will explain today. The whole idea here is to, let's say, have the engineer, the designer, spend more time into added value tasks, like analyzing results and trends, and not doing manual changes in design at every iterations. So if you look at what all the companies are doing today when they're using simulation, when you look at this graph where you have objectives to fulfill, requirement to fulfill when you're designing a product, you would do what we call a step-by-step or trial and error approach, meaning that you will start with the first baseline design. This is this red dot here. And this baseline design is maybe a kind of carryover from the former generation of your product, or comes from intuition from the designers, from the engineers, because they already designed the product. So you would start from this design. You would create from a CAD, for example, a simulation model. You would apply your simulation methodologies, and then you would assess how it behaves, how good it is against the different objectives. And based on that, you will do small steps, right? You will do some changes in the design, changes in the materials, all by hand. So even either coming back to your CAD modeler or coming back to your modeling environment and make changes manually, submitting the different simulations, extracting the results, and again assessing how it behaves. So doing this way, of course, does work. You slowly but surely improve the design if you do a good analysis of the result. But at some point, you will stop, because doing too many, you will be somehow lost with too many data, maybe, or you don't have time to do more. But the question is, have you really reached the objectives, right? And you never know, because you had only a chance to do few iterations. And also, because we have to admit that our human brain cannot analyze results when you have too many changes at a time, you will do changes of very few parameters, while your products have many design parameters from shapes, from materials, as I said, thicknesses, anchor point, or connection with other products, and so on. So as an engineer, you won't be able to change many parameters. So you won't be able to explore different combinations of those parameters. On the other side, if you use what we call the direct parametric exploration technology, well, you will target first on defining what are your objectives, what are the parameters that you will be able to play with, and then this is where it changes. You start from your baseline design, but then based on your input, you use some smart search technology, automated, that will cover the design space and bring you back more solutions that you'll be able then to make trades off from them. You will be able to make a selection. You'll be able to share more solutions, possible solution to the team, to the product team, and make the right decision. Also, with such technology, you'll be able to address more parameters. And again, the more parameters you play with, the more chances you have to find the best combination of them. So this is what we'll be diving into more today. So if you look at this system here, it's a cooling system for some electronic components, and what you try to do is to improve this system, right? And improving meaning you want to improve the thermal, the cooling behavior, the cooling performance of this cooling system, and at the same time you want to reduce the mass. In that particular example, mass being attribute which is very important in many industries. And the parameters are actually the following: is the fan, which is this black part on the upper right, the heat sinks, so those little pins that helps to dissipate the temperature, the thermal fields, and then you've got the vents from which the air is the forced air is being evacuated. So those are parameters you could play with, and again, starting with your first design, you will build your simulation models, your modeling environment maybe, submit first simulation, and then extract results based on how it behaves. Again, you will do some changes maybe on the vents, geometry or locations. You will do some changes, and again, you'll improve. But now, if you look at this, in this approach where we have created automation on top of the initial model, then you can, as you can see, explore much different avenues, much different combination, even changing the geometry, as you see, of the heat sinks, the number of those pins, and so on. And what you see on the right, this graph with those little dots, red and blue, those are the different designs that are being evaluated. Again, once everything is automated, everything is running in the background on your laptop or on a remote machine, cloud. And again, you'll spend more time into analyzing the best design that's been found by the technology, and you spend less time into changing by hand for every iteration. Again, the variables, changing the value, changing the geometries, and so on. As an outcome, in this particular example, we've got a drastic improvement in mass and in cooling performance as well. Well, you could say, well, maybe I could have found this design, maybe not. But again, it is already very complicated to change many things at the same time. You see that here the heatsink geometry has changed, but also the fan location and so on. Now we have a rough idea of what we could do with automation and smart search technology. Let's look at how Heeds MDO does address that. So what is Heeds MDO? This is what we call a multidisciplinary design analysis and optimization software. It's an open platform, as we will see, that will help designers and engineers to find more, I should say, satisfying solutions for meeting the requirements. So now you may be familiar or not with what we call the Simcenter portfolio solution. So the Simcenter solution is let's say divided in three main families: system simulations with, for example, Simcenter ACAM, mechanical simulations, CFD, like Simcenter 3D or Simcenter SAM Plus, and also physical testing with a different software to help you to gather data from a real experiment. Heeds, as you can see, is on the vertical side of this slide, is a transversal tool, meaning that Heeds will be able to automate the execution of those different tools, automate them, but not only, right? With Heeds, you will be able to create automation and exploration on Simcenter. But also, as you see now, Heeds is a very open environment where actually we have direct connection to a large number of CAD and simulation software you see in the list from different vendors. So it's a list which is changing twice a year because we are increasing the number of connectors we're developing. And you may recognize some of the tools that you're using, or maybe some of the tools that you don't use are not there. no problem. We have in this red circled window at the bottom of the slide, we have what we call a generic connector, which can help you to basically connect any software, even in-house software you may have developed, provided that they can be executed in the command line, and provided that we can read the input and output files from those simulation tools. So again, those connections, those connectors help to execute automatically a tool, execute their journal, so the different tasks, help to automatically extract data, pictures from contours, for example, or tables from or charts from the results out of those tools. So the idea is that we try to make it easy to create automation and leveraging your current tool being used in your company. So there are four, let's say, key pillars in Heeds that are being leveraged to create automation and design space exploration. So the first is the automation part of things. You've got this little video that is showing you that we have this all these connectors, as explained, and with this drag and drop approach, you will actually capture in Heeds your current workflow, your current tools that you're being used for a certain simulation. So that could be, you will start from a CAD, then you will push it to the CAD to simulation tool, then you will extract some results and go to another simulation tool to simulate maybe a different physics. And at some point you may do some specific post-processing in Excel. All of that you will teach it to execute it, and once it's executed from left to right, you will save it into templates. So that's how you're creating the automation. Just basically re-executing what you're doing today by hand, we capture it into Heeds. You can see here that we can do serial execution, but also we can do parallel execution, meaning that for a given design, we can tell Heeds, evaluate its performance in terms of CFD flow, for example, and at the same time, evaluate the same design for thermal or mechanical requirements, and then other analysis. So that means serial or parallel execution of different physics. That's the first part. Again, once you've done this, you have captured this workflow. This is saved in a template that everyone could use. That guarantees that everyone is using the same approach when using a given methodology to get to the digital twin. The second key pillar is that we want you to make it easy to leverage any computation power you have. So you'll be able to select for each software that is being used in the automated workflow where you will run it, either on your desktop, laptop, or on a remote cluster machine or another Windows machine. So we have everything set into Heeds, such as you can connect to a remote machine through different protocols. If you're using some job schedulers like PBS, SF, Slum, or others, we have those installed already inside Heeds, such as Heeds would submit the jobs, the different runs to the scheduler. So once you've created the automation and defined your strategy where you will run the automated workflow, you will define a strategy of how you will search the space. Here we will focus on driving and using our proprietary search technology called Sherpa. And this one will help you to perform what we call single objective optimization tool or multiple objective optimization. Basically, you will define objectives, you will define constraints, and of course, you will define parameters with lower and upper boundaries. And those parameters could be any parameters in a CAD file, so that could be shapes, CAD parameters, or any parameters you have in a simulation file. So that could be basically anything you have in your model. Last but not least, this is the last pillar, and this is actually where our engineers and users are spending time. They're spending time not in changing manually parameters value for each iteration. They're spending time into analyzing the results that came out of the study. And you can see in that video that actually everything is self-contained in Heeds post environment, where you can visualize for each design that's being evaluated everything you asked when creating the automation. So that could be just tables with values, that could be contours, that could be graphs. Everything can be synchronized again in single windows, and you've got multiple tools to mine into the data, help you to understand the trends, and narrow down to the one or more efficient design you would like to submit to the other people involved in designing the product with you. So that's the idea. Again, spending more time into analyzing results and understanding trends rather than spending time into changing by hand the value of parameters or shape of a part. Talking about exploration itself, one of the key components, of course, is to leverage optimization techniques. And here Heeds come with the specific ingredients. Just to make it, not to make it too long, the idea is that we want to oppose our proprietary approach to what is traditional approach that you can find since more than 20 years on the market, one with another. And this traditional process actually has, let's say, numerical limitations, to make it short, in a way that you won't be able to tackle the complexity of a real model. It means that if you start from your real model, immediately you will be asked to make some simplification, meaning either reducing the number of parameters, which means that you will have less chance to find a good combination. The fewer parameters you have, the less chance you have to have a good performing design. Or you will be asked to create what we call a surrogate model or response surface model. Some of you may have heard about that, which is a mathematical approximation of your real model, which requires to learn and which has to be handled very carefully because this is an approximation of your real model behavior. Then you will have to select an algorithm. And the good news is that there are lots of good optimization algorithms coming from the academic world. But the bad news is none of them works well for every problem you will be willing to solve. So you will have to build your own expertise to know which algorithm to use and when to be efficient. The second bad news is all those algorithms, they come with some numerical parameters you will have to tweak. Somehow you will have to optimize the optimizer. So everything is feasible, of course, but all of this distracts you from your goal or for what you're being paid for. You're being paid for designing product, right? Not to, let's say, leverage, learn how to use algorithms. Eventually, you'll conduct the search. You will get some improvement, hopefully. And when you isolate one design and you take the value of those parameters and you inject it back in the real model, what happens in many cases is that the real model doesn't behave as predicted because maybe the approximated model you've created at the first step was not accurate enough. So what you see here are those, or let's say, quotes from companies who have understood the value of automation and exploration and optimization, but they've seen that it creates a lot of complexity. It can even create errors, and at the very end, not everyone could. Not everyone could use it. So that's where Heeds came from. Heeds came with this search technology that makes it easy while very efficient to search the space. Basically, with the Heeds integrated optimizer, you'll be able to keep your real digital twin, your real model, defined as many variables as you need, and the technology will handle the complexity without increasing dramatically the time to solve that problem. And this is proven by lots of different clients using this technology. I must say that we have in Heeds also the other methods from the traditional process, because we can, people who know how to use it could benchmark inside Heeds with our own optimizer, but also this could be used in what we call robustness and sensitivity analysis. But again, let's say, to put a figure, 95% of our clients using Heeds, they're using our integrated optimizer called Sherpa. And this Sherpa, just a slide on it, is a search framework. So in Sherpa, actually, you will find maybe 20, if not more, of those best-in-class optimizer, academic optimizer. They are in there. But then Sherpa is using them in a specific manner, which is called hybrid and adaptive. Basically, what it does use all the bests of those optimizers at the same time guaranteeing that it will search globally the design space and will be efficient into narrowing down those good designs. At the very end, you don't have to focus on the mathematics of the optimization part of the approach. You just have to focus on how much time you will allow Heeds to conduct the design space study and how much time you will get to solve the problem. So Heeds will adapt to the budget you're giving and will search the space and do its best to improve the design given the time allotted here. This is a start and stop process. Example, if you have 3 days before your next design review, you know that each design being evaluated with your simulation software needs 1 hour. You will need then 72 hours to conduct. You will have 72 hours, right, before the next review. It means that you can tell Heeds, okay, now you solve this problem. Those are the objectives. Those are the constraints. Those are the parameters with the lower and upper boundaries. I allow you 72 evaluations, and you will adapt. You will adapt to search the space, and will give you results. From this, you will share improved results during your review, and you may extend. You may have some more time after this review, and you will be able to give another budget in the same study, and Heed will restart based on what it has found. And using this new budget, we'll try to improve again and search the space to evaluate if there are more performing designs. So this is very an engineer-oriented tool because again you're in full control of the time. Also, a very interesting feature is that you, as an engineer or designer, you have intuitions, you have experience, of course, and of course, this is how you will be instrumental into creating the study, into defining the parameters and the boundaries, into defining what is you want to solve and so on. But also you can submit to Heeds at the beginning of the study or at any time of the study your own ideas, so your own design, and Heeds will evaluate your designs, and whether they're good or not, it will help it to search the space. It will give it some indications. So Sherpa is not just like a cold sampling algorithm, just sampling the space. Actually, Heeds Sherpa is learning during the search of the space. So this could be put into the category of those machine learning technology because again, it will learn from what it finds during the study. So let's dive now into a detailed example. To give you a little bit of what are the different steps when creating a heat study. And after that part, we will cover quickly some different applications. So here we'll be focusing into designing an electric motor. And for that, in that particular example, we'll be leveraging Simcenter MotorSolve. Traditionally, what you will look for is to increase the torque density and the efficiency and minimize the torque ripple. So this is what you're looking for. And what you would do is, again, create your digital twins, so your simulation models. In that case, this is a 2D approach, but it could have been 3D, of course. And then you have variables. But if you do a manual approach and you have 10 variables, you will have hard time to, change them. Well, you won't change them all at the same time, because if you do so, you won't understand which variables had impact on the performance. You will change one variable's value and see how it goes, and based on result, make some other changes. So you're doing baby steps. Here, if you automate this using Heeds, you will automate the process. In that particular example, Heeds will drive an orchestral execution of MotorSolve, and looks like we'll be also doing some automating the execution of Excel, in which some post-processing is being carried over. And this is what you see now. These are the different steps. You can see on the upper left, this is the different Heeds that started from the baseline design and is pushing and solving it into MotorSolve, extracting the results, push it to Excel, being executed where Excel is extracting and some graphs. And based on that, Heeds is looking at how it behaves against the objectives, and will change again the geometry of the motor and so on. And this is what you can see on those graphs. Heeds will be looking at the KPIs, so all the objectives you're looking for, and will adapt the geometry, adapt the search in the space to improve, again, the performance. So again, all those things are running behind the scene. You have access to the data. You don't have to wait until the end of the study. You have access to the data at any time. You can pause it, stop it, as we said. You can extract the value and so on. Or you can let the study run behind the scene, and you'll be suddenly busy into doing something else. Again, in the meantime, Heeds is doing the work for you based on your input. Of course, your input is very important. In that particular example, 450 designs have been evaluated. You don't imagine you would do that manually, because you would be lost into the where is my data? How could I post-process that in a consistent manner? So here, 450 evaluation being done, and for the matter of really searching the design space and finding the best solutions. And best solution with an S. Again, the idea of design space exploration is just not to look at this yellow one, which is the best design. Actually, you will look to the yellow one, but at the same time, you will look at those blue dots which are next to it, because all of them looks to be very important, very good, with the fact that you improve the torque. You want to increase the torque density and decrease the torque ripple. So the idea is that it's giving you not just one design, but multiple designs from which the team can make decision, because the best design, this yellow one, might be the best design from the engineering standpoint, but maybe the one just next to it, which is performing well as well, has maybe a different geometry, and then the purchasing department or manufacturing department will tell you, well, this one is way cheaper to produce. Then this is the idea again. Design space exploration gives you more performing designs from which you can make a final decision. Now let's look at different application example. You could use Heeds to help you to calibrate models, your simulation models against tests. So we have a specific feature such as we can, if you have curves, as many of you want, you have some experimental testing, you can put them into Heeds and then make such that you improve your simulation model to match the curves. It also says in that example that here it's not about model calibration here. It's about designing a rubber mount, which is this part which is isolating the engine of a car from the body in white. And this rubber mount has a nonlinear behavior, meaning it has a certain stiffness, force displacement curve when it's moving from right to left and from left to right. So the requirement here is to match those lines that you can see, those solid lines, the red, the blue and the red. And you would then run nonlinear analysis in that particular case. So again, this is a small component, but actually this is a complex geometry. And if you would do that by hand, again, you will start with the first design, see how it goes, and try to make some baby steps iteration. Each time you have to change by hand the geometry and so on. On the other way, if you parameterize the model inside a CAD system or inside your model environment, if you can, like in Simcenter 3D, for example, then you can do an automatic search. And in that case, Heeds will change automatically. The shape, as you can see on the video, and will makes it best to match the two solid lines. So minimize, let's say, the distance between the actual behavior of a given design, such as it matches the solid lines. So this is an example. Another one I wanted to share is calibration. On a quite hot topic about batteries, a lot of focus now in the industry, ground transportation, but not only on batteries. And batteries are a very complex model itself. And here is Heeds is being used to calibrate the behavior of the simulation model to some experiment. Still in the electrification trend, here it's more at the system level. We will be talking about how to have an electric vehicle which has stronger acceleration, so let's say performance, but also has a maximum range. And those are two conflicting targets. I'm sure you're working every day into designing a product where targets are conflicting. I want it more robust, but I want it also I want it to have less weight. So those are typical conflicting targets, and that's very difficult to solve. So here we have as a base, as a simulation model, we start with a Simcenter ACAM model in that particular example. And the objectives are well defined, as I said. And here we will be playing with 4 or 5 variables. So those are 5 variables you can, of course, access from the ACAM model. And Heeds will explore again the design space based on the different hypotheses that have been set by the user, and we'll explore the design space and find for you solutions or the families of solutions that meet the requirements. And if you look at on the upper right of the graph, you can see different clusters of solutions: red, green, dark green, and pink. And actually, those are all good solutions. They are what we call on the Pareto fronts. This is the front where you cannot move beyond, right? You try you cannot do better than that, but all those designs are good. They're just clusters of different designs. So the red circle one of obviously the most, let's say, performing cars, but they have a lower range, while on the pink cluster is more, well, maybe more moderate on the performance, but has a wider range. So this is typically this kind of value that brings design space exploration. It gives you more ways to make a trade-off or decision between different solutions. And for that, it is all based on data, not just intuition. So behind all of that, you have all the data available in Heeds that are defining every design. I've selected this example here where actually this is still using simulation, but not only for the purpose of designing a product, but also for the purpose of improving a process. So here we're talking about injection molding on a particular product, which is a C-ring from Becton Dickinson. Heeds here is automating the simulation, which is being carried over with Autodesk Moldflow. And design variables, as you can read, are variables that come from the process itself, right? Injection rate, pack time, cooling temperature, etc., with some tolerances. And as a result, here using Heeds, not only you will improve the product because the final mass is still within the baseline, but also you will improve the process time, and this by more than 30%. And this could be key, right? Meaning that if you reduce by 30% process time, you will produce way more parts per day, and so on. So that's a great return on investment. One of the last examples I wanted to share with you. Here we are dealing with some bigger system. We're about designing turbines, and we're focusing on the combustion chamber. So this is where actually there is a lot of heat, and there are some hot spots, and those hot spots, there are potential line cracking will appear over the time, right? And usually what the designer would want to do is try to minimize those hot spots, and for that they're playing with the dilution holes geometry. Dilution holes being how in the end how the fluid will be pushed into the combustion chamber. So the geometry of each diffusion hole will change how the flow will be put into the chamber. So this is quite a complex problem and quite a long time to solve. And that particular client, they were actually doing things by hand, doing manual iteration. So they would start with the first geometry in PTC Creo in that example. They would then export the geometry into Simcenter StarCCM Plus, create the the CFD fluid thermal analysis, they would extract the temperature field and integrate it as starting point for thermal stress analysis in ANSYS. Doing such, they would do maybe a couple, 5, 6, or 7 iterations. It would take too long. And, well, they would improve some and that would be done. Then they went into creating automation with Heeds, as you can see on the videos. And then they leverage Sherpa to search into the design space and search the best digital geometry for meeting the requirement of reducing the hotspot. As a result, and in a very limited time, okay, maybe they've put a lot of computation power, but you can find some when using some clouds. They could reduce in a matter of less than 2 weeks by 18% the max line temperature on that system. If some of those of you are working more in the aerospace, well, Heeds is agnostic of any application. You understand that now. Heeds is actually executing and orchestrating execution of different tools. Those given tools are executing the simulation. Here, we're dealing into designing an aircraft wing and quite complex simulations because you have to deal with lots of margins of safety in terms of constraints. You have a lot of requirements and variables are could be, like in that case, the stiffness variables that you can see on the video. It could be also the wing skin. And here what Heeds does, it does explore, again, the different geometries and thicknesses for that particular wing to meeting the requirement. What is interesting to look on the graph, so the plots you can see, it starts with, if you can see it, it starts with a red point, meaning that the first design was not feasible. It was violating one of the constraints, certainly on the margin of safety. But anyway, that was the starting point. That was the baseline design. And you see that here we're tracking the mass because, of course, we want to find a good geometry for the wing, but with reducing the mass. But you can see that at the beginning, Heeds is increasing the mass to try to find feasible design, and it starts to explore and learn from the design space. And then you can see that from, let's say, iteration 80, it starts to have a mass which is lower than the baseline and start to find feasible design at the same time with lower mass. So again, Heeds will learn over searching the space. It does it pretty well. If you have good ideas, as I said earlier, you can inject your own design and help it to go even faster. I think this is the last example I wanted to show you is you can simulate for product, you can simulate for processes, but also you can simulate also how to improve the layout of your plant, production plant, or logistics, or warehouse. And for that, you could use plant simulation from Siemens. And with plant simulation from Siemens, this is a discrete approach, discrete modeler and solver. You're able to simulate the behavior over the time of your assembly lines or production line and so on. But you could, so once you have your simulation model, then you could use Heeds as that exactly the same way as we've defined earlier. And Heeds will help you actually to find the best layout or timing and so on to improve the performance of your production plan line or assembly line or warehouse. In that particular example, the outcome of this study was tremendous actually, because it was a reduction of material required, reduction of containers required, but also, as you can see, 20 minutes per day of production time, which has been saved. That's enormous in terms of how much euros it means for the company. Right. I think this is the end of this presentation. I just want to, again, summarize with the fact that all companies operate here now using and leveraging simulation. That is fine. But now we can bring you to the next level. Again, creating automation means that you will be able to capture repetitive tasks on those, maybe for the product you're doing, maybe some of the tasks are always the same, right? You've got a new client request, you will perform the same simulation, and all by hand takes time. You can capture it and automate it. And then you can leverage smart search technology. And we here with Heeds Sherpa technology, we make it easy and efficient to search the space. You don't need to be an optimization guru to use that, and you can be you can trust this is a very well working technology being used by many companies across the globe. Key pillars, as I said, you start with creating the workflow to automate the process. Then you will define your strategy where you will run this process. Could be a combination of local running computing and remote computing. Then you will define the search problem you want to use for exploring the space. And last but not least, you will use all the data mining tool, post-processing tool you have in the Heeds post part to discover the best design for your company. As I said, Heeds is being used by very different clients from different territory for different applications, different industries, but all come with the same, finally the same word is that this is a very easy to use solution, but easy doesn't mean, inefficient. It's easy and efficient to use. And I said easy because actually when you start using Heeds, you start with thinking about a first pilot project. You will just need 1 day of training. It's not like six days or 1 week. It's just 1 day of training, and you'll get all necessary to be able to use the whole Heeds solution. And then usually you would buy, along with the training day, you would buy 1 or 2 training mentoring days, which are where we will help you to set up your first design exploration project with your own tool on your own computation machines and so on. And from there you will conduct this first project, and you will be able to measure KPIs. And KPIs for Heeds, it's not about do I have can I simulate a crack or simulate a turbulence model? This is not Heeds part. This is the solver part. Heeds part is I would do that in the past. It would take 1 week. Now it takes 1 day. This is a KPI. So development time reduction. And the other KPI, of course, is about the pure performance. I could not find a performing design. With Heeds, I found a design which performing 30% more. I don't know. This is the kind of KPIs you will measure and help you to create a business case for investing more in Heeds in your company. All right. If you have any questions today, I would be happy to answer them. If you have questions later on, you can contact Raymond Keringer from ACAM. We will address that. And I would like to thank you for the time.